So good afternoon. First of all, I would like to thank the organizer and especially Fernando for giving me the opportunity to give this lecture during this nice special year. So I'm going to speak about a technique developed with Tristan Rivière in order to get some weak compactness for some problem which get some conformal invariance. So in fact, the technique can be applied to many problems, but for the sake of simplicity, today I'm going to speak only of two cases. So the first case is a very general setting in dimension 2 for second order problem. And since, as you know, in dimension 2, the conformal group is bigger, and then the equation will be simpler, and the idea will be simpler to spread. And the second case I'm going to speak today is the conformal equivalent, conformal generalization of minimal surfaces, namely Willmore surfaces. So my talk is divided in 4 parts. First, I will get an introduction to conformal invariant problem. Then we will prove a very general energy identity. So this is for the first hour, I guess. And then I will give some basics about Willmore surfaces, and I will get some compactness result about Willmore surfaces. So the idea is to give a very detailed proof of the first case, which is in some sense the baby case, and then to explain during the second hour how we can apply this strategy to the second case, pointing the difficulty. So let's start with an introduction to conformal invariant problem and with an example. So example, the CMC equation. So CMC stands for constant mean curvature equation. And so let's back to the 19th century with a very classical problem, the Plateau problem. So given a curve, an R3, we try to find a disk which spans this curve and with minimum, whose area is minimizing. So we try to minimize the area functional among the space E of W12 map such that the boundary is sent to the curve. If you consider this problem, you are faced to the first difficulty is that A is invariant under the group of diffeomorphism. So if you pick a minimizing sequence, there is no chance for it to converge because of the action of this big group. So the idea of Douglas and Rado in 30s is to replace A by the Dirichlet functional. The Dirichlet functional is only invariant under the action of the Möbius group. Which is smaller, it's a finite dimensional group. So you can, Douglas and Rado managed to minimize this functional, and also you have to remark that if you have a critical point of D, it's also a critical point of A. So, and then you can compute the Lair-Lagrange equation, which is Laplace U equals 0, and U conformal. That is to say, Ux uy square equal ux uy. And of course, u then is equal to, it's an equality here, sorry. And so critical point and minimizer satisfies this equation. And so the regularity is not a problem now because you are leads to the world of harmonic maps. It's quite, but you can look to some variant of this problem, especially the soap bubble problem, which consists to minimize this functional, but under a constraint. That is to say that your disk has to enclose a given volume. So you replace your space E by E prime. So the space of W12 map from the disk to R3 such that 1/3, for instance, of the integral of ux wedge uy dz equal 1, and of course you still send d to gamma. So if you minimize d over this space, you have a new Lagrange equation, and critical points are the well-known constant mean curvature surfaces, which are a solution of the isoperimetric problem. It's a kind of isoperimetric problem with boundary. So the equation, it's appears due to the constraint, a Lagrange multiplier. And you still conformal so this is known as the CMC equation. And this equation is much harder to deal with from an analytic point of view for two reasons. The first one is you have a nonlinearity here. So it's a nonlinear equation. But the main difficulty for me, from my point of view, is that due to this wedge, you have a system. It's a strongly coupled system. In particular, you have no maximum principle. So if you need some new techniques in order to have regularity, even existence of this equation. But we have some theorems. The first one is due to Hildebrandt in the 70s, which states that if your curve is small enough, then, so I'm going to give a name to this equation, E lambda. This one is, of course, is 0. So if gamma, the norm of gamma is smaller than 1, then E1 has a solution. Then, in the 80s, Bresis and Coron prove that if gamma is strictly smaller than 1, then E1 has at least two solutions. And this was proved using some mountain pass technique. And the idea is the following. The sphere, the round sphere, is a CMC1 surface. And if you have a curve on this surface, which is not equatorial. That's why you have this restriction here. Then it is spanned by two CMC surfaces, the small one, the small spherical cap, and the big one. But in order to convince you that this problem is hard from the analytic point of view, so as I have already said, there is no maximum principle, and in consequence, there is no Alexandrov principle. So it's really hard to prove that the symmetry of the boundary occurs in the interior. And the following conjecture is still open. If gamma is a circle, then there is exactly two solutions, which are the small and the big spherical cap, bounded by this circle, except if you are in the, of course, if the norm of gamma is strictly smaller than 1, else you have exactly 1, which, because it's symmetric with respect to the equator. And so there is no maximum principle, but there is another tool which is fundamental in the analysis of this problem, which is a lemma due to Wente, it's a German, 69, which is a very deep tool in order to prove the two previous theorems. So let A and B some W12 map from the disk and phi W110 such that you satisfy the following equation. Laplace phi equal Ex By minus Ey Bx. Then the regularity of phi is much better than expected. In particular, phi is in L infinity, and you can control the L2 norm of its gradient by a universal constant times the energy of A times the energy of B. So this is one of the fundamental tools in order to study the CMC equation, for instance, and all conformally invariant problem. Yes?
In the conjecture, you're making the normalization that integral has to be equal to 1? What's the
No. If so, for CMC equal 1, for E1, in the conjecture, if it is 1, it is known. It is known that it's the spherical cap. In the critical case, it's okay. With some flux argument, you can prove that the spherical cap is the only solution. But here, the conjecture is open if you are below the equator.
So you want CMC equal to 1?
Yeah, CMC 1. So I put 2 lambda because the CMC equation lambda equal h. So this is a model equation, and for this equation, the regularity is much better than expected. Of course, it's due to the Jacobian structure. It is false if you just have some nabla u square criticality, like this. You can check that u equal log of z over r minus log. You have to fill the boundary condition. 1 over r is a solution. Of course, a log is not bounded in L infinity. So I'm going to give you a short proof of this lemma because we are going to use it a lot. So, in fact, it is easy to see that The L infinity bound implies a W1 to 1. You just multiply by phi and you integrate by part. So now we are going to prove the L infinity bound. For this, we have to take advantage of the Jacobian structure. So we rewrite the right-hand side as A B theta, so in polar coordinate over A B R theta over R. We make appear some divergent structure. And then we are able to compute the value of phi at 0 by using a green formula. A B theta R minus A B R theta dr d theta. And then we integrate by part. Of course, this term disappears. Since the integral in theta is vanishing over every circle, then we can subtract the mean value of A. Then we apply Schwarz inequality, and then Poincaré inequality, because the L2 norm of this on a circle is smaller than the derivative. And it's over. So yeah, let's assume that A and B are some smooth functions. Sorry, you integrate. We don't. By density, it doesn't matter. 0 of 2 pi, so A theta B theta, and you have, of course, B. So, but, and after you apply once more Schwarz inequality and it's over. But I do the proof because I want to use a fundamental property of this equation here. So I just estimate the value at 0. But in fact, the Mobius group acts transitively on the disk. And the equation, due to the Jacobian structure on the right side, is invariant by the Mobius group. So the estimate at 0 is variable for every point, in fact. So, which implied by action of the Mobius group implies that the L infinity estimate. So this is a fundamental tool of this kind of analysis. And now, after this introduction, I'm going to speak introduction about CMC equation. I'm going to speak about conformally invariant problem in general. Not in dimension 2. So we consider a Riemann surface. And N a submanifold, a closed submanifold. And we look to functional LU equals the integral of a sigma of LU nabla U dV. And we want the functional to satisfy two properties. Of course, the first one is to be conformally invariant. So for every conformal diffeomorphism, conformal map, let's say with degree 1, we want that LU of phi equal LU. And the second property is that we have a critical growth. There is a C such that P square of a C is smaller than LP smaller than CP square. So of course there is many functionals that satisfies those property. I will just speak about three fundamental examples. The first one is the energy itself. Whose critical point has the so-called harmonic maps, and whose equation is Laplace U equal AU nabla U nabla U, where A is the second fundamental form. Second example is a generalization of the one we speak before. So we consider the disk, the target being R3. And so yeah, R3 is not closed, but it's not a problem in here. For harmonic maps, it has to be closed for the rest of the talk, but not for CMC equation. So R3, and you pick a function h from R3 to R. And you look to the following functional. EU equal 1/2 of sigma nabla U square is V plus 1/3 of QU UX wedge UY. TZ. And Q is a function such that the divergence of Q equal H. So this problem is known as the prescribed mean curvature problem. It's a generalization of the mean constant mean curvature equation. The existence theory for this problem is not solved today. I mean, not for the disk, but for the sphere. We don't know exactly which are the functions we can prescribe as mean curvature. And so prescribe and the equation is Laplace U equal -2 HU UX with UY and U conformal. I would like to make you note that here we lost the structure because we have this HU. If H is constant, it's okay, but else it's not, you can't put it in divergence form. And the last example is when N I get more structure, like it's a Keller manifold. So you have a symplectic form. You can pull back the form. It's a two form, so it becomes a two form on your surface, and you integrate it. It gives you a functional whose critical points are the so-called G holomorphic curve. Whose equation is the generalization of the Cauchy-Riemann equation. So these three problems share some common characteristic. The first one is to be critical. Critical with respect to the elliptic theory. So equations are like Laplace U equal nabla U square. Even the last one, because you can make it like a second order equation. So nabla U square, because we work in the space of energy, is only in L1. You have no LP theory, so no a priori estimate. But the more obvious remark is that all these equations are conformally invariant, in the sense that if U is a solution, at least on the disk, but locally every surface is conformal to a disk. If U is a solution, then U lambda is a solution. So you have concentration phenomena. And I would like to give you some heuristic of this phenomena before to go through the details. So we are going to consider sequences which blow. So UN sequences from the disk to R3 to sequences of solution, such that nabla UN blows at 0. So your sequence is not bounded, so what you can do is to rescale it. And now the gradient is bounded. And so you converge to some limits, to some solution. But since you rescale your domain, now you converge into C2 log of R2. So this solution is the solution of the limit equation when you blow the domain. It's called a bubble. And we can also assume that far from 0, everything is OK. So UN also converges to U infinity in C2 log of 0. Of the disk minus 0, sorry. So I'm going to make a picture of what's happened. So far from 0, we very well understood the behavior of UN. And close to 0 at the scale lambda n, we also understand very well this behavior. And so here, at scale. So this is a domain. Far, we understand, we converge to a limit solution. And at the scale lambda n, when we scale, we go to a bubble. It's called a bubble because for CMC, bubbles are round sphere. And the question is what happens in between when you are close to 0 but far from lambda n. You have to glue your two solutions by a neck. So that's why this region is going to be called the neck region. And the most natural question you can ask is, does we lose energy in the neck region? So, for instance, do we have limit of the energy of UN equal to the energy of the limit map plus the energy of the sphere, of the bubble? So this is what we call an energy density. And we are going to prove that there is one for every conformally invariant problem during the second half of this first hour. And now, so I come to the proof of this, but I will give a precise statement before, don't worry. So this was just an heuristic, of course. And but before that, so we have some weak version of we can write in a general way the Euler-Lagrange equation satisfied by all these functional. So it's a theorem due to Grütter and Rivière. If U is a critical point of a conformally invariant functional, then you satisfy, then there exists omega, a one form in L2, which take value in the space of antisymmetric matrices. And this is the key point of all the analysis. Such that you satisfy the following equation. For instance, for the case B, for HU is omega is HU times, so it's an antisymmetric matrices U2 here, the P1. And this matrix is viewed as a one form, and nabla perp is just minus dy dx. So every Euler-Lagrange equation of conformally invariant functional can be put in this form with some anti-symmetry here. And Hildebrand states a conjecture that every critical point of a conformally invariant functional must be smooth. And in fact, what proved Rivière in 7 is that if you, so let's say in W12 is a solution of star, then the regularity is better than expected. That is to say, then U is in W1P for all P bigger than 2. I will show you this, give a short sketch of the proof of this theorem in order to introduce some tools. So here the idea is to rewrite the equation star into the 1T form. So and for this, you need the following theorem, which is some kind of nonlinear Hodge decomposition of the omega. If so, there exists theorem, and here the antisymmetry is fundamental. There exists epsilon 0 such that if omega is smaller than epsilon 0, then there exists A space. So in W12, which take value in the space of invertible matrices, and B which take in the space of matrices. So you can write the equation like nabla A minus A omega. Not the equation, sorry. B. So if A is not here, it's a Hodge decomposition, but this is nonlinear here. I will give a word about this theorem before, but just you see why I do that. Is if you plug this equation in star, star become divergence of A nabla U equal nabla par B nabla U, and curl of A nabla U equal nabla par A nabla U. So now you have rewrite the equation star into a diff curl on the left-hand side, an elliptic operator, and a Jacobian on the right side. And now you can apply 1t to get some energy estimate. Energy estimate give you more estimate, and then you have the expected regularity. And where come from the ideas of this nonlinear Hodge decomposition? It comes just from gauge theory, from Uhlenbeck work for young mills when you find a good gauge. And this is a kind of Coulomb gauge for this problem, in some sense. And so this is a very short sketch of the proof of the regularity of this equation. But what we want to do is to prove some energy density. In order, so energy density occurs when there is some concentration, and of course you can't apply verbatim these ideas, because when you have concentration, you are always above epsilon 0. So you can't rewrite your equation in this form. And you need some news, to refine this kind of analysis in order to be able to have an energy identity. So before proving the energy identity, I will introduce the last tool, which is Laurain Spaces. So Laurain Spaces, so I give a reference because I have no time to give a precise Elan books, chapter 3. So Laurain spaces are denoted by LPQ, are refinement of the LP spaces with the same scaling property. But for our interest, we will focus on L2, which is included in a bigger space, L2 infinity, known as the weak L2. And it's really bigger since 1 over R is in this space. And here have a dual, which is smaller, L2, 1. This is the only thing we are going to use. And I would like just to convince you during the talk that those spaces are the good one, to use when you are faced to some isoperimetric problem, some CMC equation. Since we have a refined 1T inequality, which is, in fact, not only nabla phi is in L2, but is in L2, 1. And this inequality, in some sense, is a sum up of the previous one because it's a fundamental, it's a property of W1 to 1. W1 2 doesn't inject in L infinity, but W1 to 1, yes. So, sorry for this bit long introduction, but I would like to define all the tools. And so the main idea of the first part of the talk is to prove an energy identity not only for conformally invariant problem, solution of conformally invariant problem, but let's try, as for the regularity of Rivière, to prove an energy identity for solution of this kind of equation. Since regularity occurs, why not we will have an energy identity? So we are going to consider a sequence of solution and try to decompose it as limit solution plus bubble and try to prove that there is no energy in the neck. Okay. So energy identity so of course it is quite unexpected, but we will see. Because it's a linear equation, and energy density usually are from nonlinear phenomena. But I take UN in W12 of the disk, which take value in omega n in L2, a one form which take value in the space of antisymmetric matrices. And such that, of course, the energy is bounded. Ah, sorry, yes, I forget. Sorry. I'm going to give a precise definition of what we look. And which satisfies this. Sorry, I only give.
Where is the lambda 1 d there? Where is the?
Sorry.
Just trying to understand the algebra there. Where lambda 1 d in your equation?
It's a one form.
Yeah.
So one form, lambda 1d is one form on the disk, and it takes value in the space of anti-matrix. It's a matrix of one form, an anti-symmetric matrix of one form. So here, you look at nabla un as a vector, and it takes vectors. Yeah, I've give you an heuristic of energy density, but you deserve a full definition. So it should occur before, but definition. We say that a sequence UN satisfies an energy identity if, so of course there is not only one bubble, there can be several. So there exists U infinity, a limit solution, some point of concentration, so a finite number, some speed of concentration, some bubbles, such that of course UN goes to U infinity when in W12 lock of the disk minus the A infinity I. If you rescale correctly UN, that is to say around the point of concentration by the scale of concentration, you converge to some omega I in W, sorry for this, 12 log of R2. And there is no energy loss, that is to say, if you subtract to UN the limit solution minus the sum of bubble correctly rescaled, then the energy goes to 0. So I will make a picture in a few minutes about the bubble tree, but so this is our goal, is to prove for this in this general setting, to prove this energy density, to be able to decompose the sequence of solution as a limit solution plus some bubble without loss of energy in between. So the proof is in 4 steps, and the first one is a well-known concept of epsilon regularity developed by Schoen and Uhlenbeck for harmonic maps, which states that, morally speaking, that under a certain level of energy, everything is under control. So here is if U is a solution of star with epsilon regularity, so there exists epsilon 0 such that if U is a solution of star and omega is smaller than in L2 norm than epsilon 0, then you can control U in LP, for instance, on a smaller ball by a constant which depends only on P times energy. And if omega is bounded by nabla U, which is the case when you consider conformally invariant problem, then you can bootstrap this estimate up to nabla U, so you can control every derivative. So up to reduce the size of the ball. So first consequence is what we call the energy gap, is that the energy of the bubble is quantified. Every bubble should have a minimum level of energy. So energy gap is if you have a bubble, so a bubble is a limit solution of the limit equation on R2, and if big omega is smaller than epsilon 0, then it forces nabla omega to be trivial. So one consequence of step 1 of the epsilon regularity is that you have a finite number of points of concentration, because if you concentrate, you need to be above epsilon 0, else you have strong convergence. Then step 2 is bubble extraction. So I will write quite quickly bubbles extraction. So this is the same. There exists some point, a finite number of point of concentration, of course. I just say it. Speed of concentration, bubbles, which satisfy the two first. That is to say, you converge to the limit. I forget to write it. When you dilate your bubble, so there exists also U infinity in W12 of the disk. So such that UN goes to U infinity. When you rescale, U goes to the bubble, of course. And you can do it. Of course, the energy is not going to 0, else it will be over. But you can ask that the energy smaller than epsilon 0 over 2, in the neck region. I will write it better than this. So what is the neck region? I say it is when you are close to the bubble but far with respect to its scale. So I'm going to write one. So the neck regions are B center here, 1 over R. So you are close to the bubble but far with respect to the scale of the bubble. And so you want this energy. So it's quite a technical statement for a very simple idea. I think it will be clearer on a drawing. So the image is just the following. You have the disk, and you have a finite number of points of concentration due to epsilon regularity. And then you pick a radius, lambda n, around each point such that it's the first radius where you start to see something, where you have at least epsilon 0 around this, epsilon 0 over 2 around this radius. And you rescale your solution. What can happen? So at the exterior of this circle, you are below, you have exactly epsilon 0 over 2. So the convergence is strong. In the interior, you don't know. Perhaps you have a lot of energy, so some other point of concentration. And you redo the process. You select the first radius where you see something, some energy, and you dilate. But the process stops. Why? Because each time you blow something, you blow at least one bubble, and you have an energy gap. The energy of each bubble is at least epsilon 0. So you have what we call a bubble tree. So it's a so here you have your limit solution. Perhaps you have some bubble here, here. Perhaps bubble over bubble, but the process should stop. Okay, this is the image. This is the parameterization. And so when you have several bubbles, things become techniques, but all the ideas are the same than if there is only one bubble. So now I consider that for the two last steps that there is only one bubble. From now only one, because they are isolated. They don't see each other. So step 4. So we have only one bubble, so it's a disk, it's centered at 0, and the scale is lambda n. And is weak estimate. It's something automatic. It's just due to the scale invariance. Is that the limit in the neck region of the weak L2 norm is 0. So it's B1 over R minus BR lambda n. In order to do that, I have just to prove that nabla un is a little o of 1 over r, because 1 over r is in the weak L2 space, so we just need to prove that. And for this, by contradiction, if we find the second Zn such that nabla un Zn is bigger than some delta, and Zn is in the neck region, very small with respect to 1 and very big with respect to lambda n, then we just rescale at this scale. So you consider un tilde equal un of Zn rescaled by the size Zn. Oh. And since you are in the neck, the energy is below epsilon 0 over 2, so you have strong convergence, no concentration. So you converge to something like this in R2 minus 0. But you can erase the singularity, of course, because you can erase singularity, the energy is finite. And you have strong convergence, so this may be non-zero because the gradient is always bigger than delta, but by energy gap, this is 0 because the energy is below epsilon 0 over 2. So by energy cap, this bubble must be 0. There is not enough energy to develop a bubble. So it's a contradiction. Ah. Gradient. No, you have your contradiction. And so we are leads to step 4, strong estimate. So that is to say, thanks to duality, you just need to prove some estimate in L21. You told me that we stop after 1 hour, or?
Yeah, with some flexibility.
Yeah, 1 hour. So I finish this proof, sure. and we stop. And so what we just need to prove that the L21 norm is bounded. And so
that's step 4 plus 1.
That
or 4 prime.
No.
You don't have a 3.
Ah, yes, there is no 3. Sorry. No, there is only 4 steps. So yes, you need to prove some L21 estimate, just a bound, because the L2 infinity norm goes to 0. And for this, you want to apply the improved 1t. But in order to have imply improved 1t, you need to use the conservation law, the Hodge decomposition. And for this, you need to be below epsilon 0. So since you have concentration, you remove the a disk at the scale lambda n in order to remove all the energy given by the bubble. And you are in the neck, and here you are below epsilon 0 over 2, below epsilon 0. So, but this is like B1, so it's a neck region you have picked, which is conformally equivalent to a disk minus a small ball of radius epsilon, which with epsilon 0, that goes to 0. And you want a 1t lemma on this domain. But unfortunately, it's false, because you have harmonic functions that doesn't satisfy the 1t lemma on this domain. So Laplace u epsilon equals 0. And the L21 norm goes to plus infinity. So, of course, it satisfies the 1t assumption. It's an harmonic function. You can always assume that, and this function is the logarithm. But what we remark with Rivière is that this is the only function that the logarithm is the only harmonic function for which you can control the L21 norm by the L2 norm. So for all other functions, it's true, especially if you consider Fourier analysis, you can control all the angular derivatives. So the lemma is the following. So 1t. So 1t assumption that you control the angular derivative by L21, sorry, by the energy of A times the energy of B. And here you have to add the energy of phi because there is no boundary Dirichlet condition. And so I'm going to conclude. So we have a theorem, but not for all derivative, only for partial for angular derivative. was proved by me and Rivière in 12. The angular derivative of solution of star satisfy an energy density. And this theorem is optimal in the sense that we prove that there is some solution which lose some energy in the neck with some gluing some logarithm part. But of course, the initial goal was not the solution of star, but all the conformally invariant problem. And I will conclude the first hour with a proof. So in some sense, it's step 5. If U is a critical point of a conformally invariant functional, so of course you have a solution of star, but there is another property because this comes from the invariance by rotation, but if you use invariance by dilation, you can see that the right hand side is always orthogonal to ux and uy. If you think about harmonic maps, the right-hand side is the second fundamental form. It's always normal. And then you can multiply the equation by ux and uy, integrate by part, and that gives you a Podzev identity, which is the integral over any circle of the angular derivative equal to the energy of radial derivative. So for conformally invariant problem, we have the energy identity for all conformally invariant problems. So theorem all sequences of critical point of a conformally invariant functional satisfy an energy identity. And here we only use the conformal invariance. And this is the key point. So we have 5 steps, and on each step we only use the conformal invariance. So that is to say, here with the anti-symmetry in the first step, in order to quantify the angular derivative, and here in order to get the Podzev identity and quantify the radial derivative. And this proof works in any setting, indeed. So it works also for biharmonic maps, for free boundary harmonic maps, and also for Willmore surfaces. And this is my goal during the next part of the talk. Thank you.
Okay, so we resume in 5 minutes.
So we proved only using the conformal invariance that we always have in dimension 2 for second order problem and energy identity. In fact, it was already known for the example I have cite, but not with the optimal hypothesis. Here, we only use the fact that omega is in L2. So it permits us to reach the best assumption. That is to say, here, A have to be in C0. So n in C2. That's improved previous result. Here, h in C0, we just need that. That is the best assumption you can expect. And for geomorphic curve, it's j in C0, so you just need n to be C1. And here, so everything I've done on disk. So on a compact surface, you can decompose your surface in small disk if the conformal class stay bounded. Else, you have some degeneration, like on this picture, and it's not possible. And so you have one part of your decomposition that is going to be a color. That is not a disk. And step 5 doesn't work in this case, because in step 5 you have some integration by part that work only on the disk. But this step still works in step 5. You don't need step 5 for geomorphic curve. You can assume that the conformal class degenerate, because ux and uy are linked by the equation, so you have an automatic positive. So I just want to say a word about what the case when the conformal class degenerates, especially for harmonic maps, because it is very well known by some work of Miao Miao Zhu, notably, that proves that you don't have energy identity because step 5 failed, but you can quantify the loss of energy in the collar. And here I insist, collars are not neck, even if they are the same shape. But neck are closed by a disk. So when you make an integration by part in a neck, there is no residue, no boundary term. But collars are bound by genus, so they are not bound by disk. And so step 5 fail. When you integrate, that says that the difference of those energy is constant along the collar, but non-vanishing. You don't know that. And so the loss of energy is measured for harmonic map by some residue of the Hopf differential you compute in this collar. But you can avoid this phenomena in some particular case, especially when if you bound the index, for instance, if the target is positively curved, because the collar, we know that they shrink onto geodesic. And if you lose energy, the length of the geodesic is infinite. So you have infinitely many Jacobi fields along this geodesic. And then if the index is bound, you get a contradiction. So that's my point. When the conformal class degenerates, there is no energy identity except if you add some extra assumption. So now let me talk about surfaces. So I will try to be more clear now with more surfaces. So a classical problem in differential geometry is what are the best immersion of a given surface in R3 or in R. So best means the less curved. Of course, the curvature we consider is the extrinsic curvature, the mean curvature, but you can't minimize it pointwise, else you will have a minimal surfaces, and we know that there is no compact minimal surfaces in R3. So you try to minimize it globally, and for this you look to this following functional introduced by Blaschke in the 20s. So if phi is an immersion, then you look to W phi equals the integral over sigma of h squared dv. I will justify this choice in a second. So Wilmore itself in 65, he proves that W phi is always bigger than 4 pi, and equality if and only if we are the round sphere. And from that time, critical point of W are called Wilmore surfaces. So why we interested in W and not another energy? Because W has this very good property that is conformally invariant. If you have a best immersion, if you dilate it, translate it, rotate it, it's still a best immersion. So it was already known by Blaschke that if theta is a generic Mobius transformation, then W theta of phi equal W phi. Generic means that if there is an inversion, the point of inversion is not on the surface. Of course, else you lose some multiple of 4 pi of energy. Sometimes some people prefer to look to this functional, which is strictly equivalent to the previous one, because it differs from it by a topological term, which is just the integral of the Gauss curvature. But it's usually they prefer it because not only this one is conformally invariant, but the integrand is conformally invariant, which is quite important when you apply directly Noether's theorem. So let me review some results about Willmore surfaces. So when sigma is a sphere, then in R3, we have a complete classification due to Bryant, 86, I guess, which asserts that a Willmore sphere is the inversion of minimal surfaces with planar end. And with, sorry?
You wrote R4.
Yeah. Because I was thinking about the next result, but with K planar end. And so that means that the energy is a multiple of 4 pi. And there is some K's that are impossible, which is 2, 3, 5, and 7. In fact, the result is also true in R4. It's a result of Montiel. But since and there is also a result I will split later about branch Willmore sphere, which are important for us because the limit of the bubble are possibly branch, and due to Rivière and Mishla, but I will speak about this later. For when sigma is a torus, of course, we have the famous Willmore conjecture proved by Fernando and André, which states that the minimum is achieved by the Clifford torus. In this case, in the case of torus, there is an interesting result of Pinkoll, which proves that there is some non-conformally minimal Willmore surfaces. So using the up vibration, non-consistent of non-conformally minimal. When the genus is bigger, what we know more or less is that minimum is achieved. Of course, there is existence by the Lawson minimal surfaces, but minimum is achieved is due to covert and in dimension 3 and Rivière in dimension bigger. It's around 10. So it's a brief review of what is known. Now, from the PD point of view, what is the equation satisfied by Willmore, critical point of the Willmore equation? The classical equation is the following. Laplace dh plus 2h h squared minus k equals 0. So here we have two problems. The first one is that, so it's a first order equation because h is itself a Laplacian of the immersion, but g depends on phi. The coefficient of the operator depends on the immersions, which is one problem. That can be partially solved considering conformal immersion. But there is a more deeper problem here, is that the nonlinearity is in h cube. And h cube a priori is even not in L1 because we work with only h square bounded. So a priori you can't make like standard PD analysis. So in order to do so, we are going to use the conservation laws, to use the invariants to get some conservation laws and to be able to rewrite this equation into a more tractable way. So in order conservation law, by using the famous Noether theorem. In fact, it was those conservation law was discovered by Rivière, but by hand. I make a big computation, and at the end there is a miracle, a divergence-free quantity that appear. But in fact, there is no miracle. It's just the conformal invariants that give it. And this is done in a nice paper of Bernard that appeared 2 years ago. And of course, I won't make any big computation, but I would like just to give you the spirit of the proof, how to derive those conservation laws. So, morally speaking, what's sorry for that. What states the Noether theorem is that to each symmetry of your functional, you can associate a conservation law. But we are going to prove it by hand. So you look to your functional, and you perturb your immersion. And you look to an expansion. And the spirit is the following, so you have W5 plus, so I'm going to write it like a vectorial approach. So H, vector H is just Hn. So when you develop, here you have an expression bunch with some second derivative of phi, first derivative phi plus, something like this. And what you are used to do is to integrate by part. That's what we are going to do, but for once, we are going to not throw the divergence term. So if you integrate by part, here you have an expression, W times phi plus t, some divergence term plus some t squared. So here you refine the Euler-Lagrange equation in a vectorial way. But Now you reapply what you do using the conformal invariance. So you assume that phi is a translation field. And that big phi is Wilmore. Since it's a translation field, it's invariant. So the first term vanish, and you just have this divergence term at the order t plus some t squared. But in fact, you can do it on any domain, because you didn't integrate by parts, so you have no boundary problem, because you keep at each step the divergence term. You never suppress it by using some condition at the boundary. So you can do it for every omega in sigma. And in fact, you get some pointwise that the divergence, and now I'm going to give you the expression of this. I'm not sure. So this is the divergence form of the Wilmore equation. It's not like m. So this is better, but you need more, and the rest is given by rotation and dilation. So we are going to call this field T. And now if you take a rotation field, you see that divergence of T wedge phi plus 2H wedge Naplaper phi is 0. And if you take dilation field, you have the divergence of T scalar phi is 0. So in particular, there exists R and S such that you can integrate those quantities. So Naplaper R equal T wedge phi plus 2H wedge Naplaper phi, and Nabla S equal T scalar phi. And the last equation is just divergence T equals 0. So this is the three conservation law given by the three invariants. In fact, I should say more. Translation gives 3, dilation 1, and rotation gives 3. And now, in fact, you have also one given by inversion, but it's more complicated to state, so I won't give it. If you play with those equations, you can rewrite the whole system as follows. So now Wilmore, being Wilmore, become equivalent to the following system. Laplace S equal minus Nabla N Naplaper R. Laplace R equal, so it's just Jacobian structure. And you have the third one, which is the one in fact given by the inversion. So and now what you note is the two first equations, the one in R and S, which are the auxiliary variable, is an autonomous system with nabla n here, which is in L2, perfect, and with some Jacobian structure. So you can apply 1T and prove some compactness by compensation for R and S. And you can bootstrap your estimate and get as much as regularity as you want. And now, thanks to the third equation, you can plug those estimates here and get some estimate on phi. Not directly on phi, of course, because the right-hand side depends on phi. But it's normal, because your equation is dilation invariant, so you won't have any uniform estimate without fixing the conformal factor. So every estimate will depend on the conformal factor. That's what is given here. And so you get some epsilon regularity. So we reach our step 1 of our analysis. And the rest, the rest is almost automatic. So, so there exists epsilon 0 such that for every A positive, there exists CLA. I will explain this in a second. Such that if, so the energy of your immersion on a disk, let's say, to simplify the notation, is smaller than epsilon 0, here I'm going to write an hypothesis which is vacuum in the case of the disk, but which is not, and which is the second key point for Wilmore, is that, so I put it in parentheses because you don't need it for the disk, but as soon as the conformal class degenerates, it's an important hypothesis. Yeah, sorry. Here I write lambda without explicit, but it's clearly, yeah. And all my immersion are conformal. Because for now, I put no metric on the, it's the classical metric of the disk. So if this is bounded, which is always the case on the disk, but not on degenerating surface, then you control every derivative up to controlling the conformal factor, of course. On a disk, half disk is controlled by a constant which depends on A times the energy square plus 1. Okay. So we have almost epsilon regularity. And as I say, the rest of the proof is not automatic, but the scheme I have presented to you in dimension 2 for second order problem works for Wilmore. Step 2, 3, and 4 works. So we just have to solve this problem. If we want to consider a surface whose conformal class degenerates, and I will explain it right now. So yes, if we solve this problem, we will have some weak compactness. That is to say, we will have an energy density. We are able to decompose the surface into a limit plus bubble. So it's, yeah, part 4 compactness for Wilmore. And here, so the key point is to control the conformal factor, and this is a result when the conformal class is fixed to L1, and I will prove it. So L1 or Muller's Veyrac, it depends on the setting. And it's independent of being Wilmore. It's just because the second fundamental form is bounded in L2. If phi is from a surface to R3, where is a conformal immersion such that the energy of the Gauss map is bounded, then the gradient is bounded by a constant which depends on A and H, the metric of your initial surface. The proof use the Liouville equation. Laplace lambda h equal exponential 2 lambda k phi minus kh. Oh, yes.
The sigma is closed in this case?
Yeah, sigma? Yeah, closed. Yeah. And I'm going to assume that we have constant curvature. But since we are conformal in any conformal class, you have a metric of constant curvature. And kh, yeah. And so this is the Liouville equation. So you can apply the green identity. So here's green function. And by hypothesis, this is bounded in L1. So this is something classical. That the gradient square controls this quantity plus kh is controlled by 1. Everything is bounded. And so since this is in L1, by interpolation you just need to control the gradient of the green function in L2 infinity, and this is true. Of course the constant is going to depend on h, on the metric here, because the green function depends on the metric. True, because the green function have only one singularity, which is like 1 over r. So, and in fact, this space is the best space where you can have this estimate. It's false in L2, this estimate, but it's just true in L2 weak. So this is the idea, a brief sketch of the proof when the conformal class is fixed. I mean, and the question is, what's happened when the conformal class degenerates? So the behavior of the green function have been a lot studied by people, notably in arithmetics, where this kind of problem is very important when you are on an arithmetic surface. And for instance, if conformal class degenerate, GH blow, because morally speaking, GH of xy is the sum of phi ix, phi iy over lambda I up to some normalization, where the phi are the eigenfunction of the Laplace operator. And so if your conformal class degenerate, at the end the limit of the nodal surface is disconnected. And so lambda 1 is going to go to 0, because here the lambda 1 is 0. And so your function is blowing. So these phenomena have been a lot studied by people like Buzzer. But as far as I know, nobody have looked to the gradient. And what we have proved with Rivière is the following. And I think it's a theorem that can be useful in another field than just Wilmore. That if sigma n is a sequence, so C is for conformal class, sequence of Riemann surface, then we can bound G. So the L2 weak norm of the gradient of the Green function uniformly, independently of the conformal class. And in fact, now, even when the conformal class degenerates, in our epsilon regularity, my parenthesis assumption becomes totally, so it's a recent theorem. And this theorem also permits to have a uniform control on the conformal factor in this weak space, and it gives some Harmonic behavior in the annulus region, in the neck region, and also in the collar region. And so now I can state the main theorem, because we have step 1, epsilon regularity. Step 2, 3, and 4 are automatic. And as I said previously, only step 5 can be a problem, because step 5, it's like Podzaev in the collar. And since I'm going to assume that the conformal class degenerates, and when I integrate my conservation law here, so divergence gives some nabla perp. It's true on any disk, but in the collar, I have some residue. And each conservation law gives a residue. Translation give 1, dilation give 1, and rotation give 1. For harmonic map, you have only the one computed by the Hopf differential. And Zhu, he proves that the loss of energy for harmonic map in the collar is quantified by this residue given by the Hopf differential. So we were expecting that the 3 will play a role, but only the 1 by rotation is going to play a role. Okay. So of course we must have some hypothesis on the residue. So it's a theorem. Let phi k from sigma hk to R3 a sequence. So the conformal class is it doesn't depend on k. It's not fixed. Sequence of conformal Wilmore immersion. Then there exists so I'm sorry, I'm going a bit to abuse notation. Conformal weak immersion and some bubbles. Oh. Sorry, I have to write the hypothesis. Such that for every shrinking curve, we have, so shrinking curve are shrinking geodesic. So we assume that some residues should converge to the right scale. 1 over the length of this geodesics times the integral over the geodesic of the third one, so it's t wedge phi plus 2h wedge nabla perp phi against the normal of the geodesic. So this limit is 0. If this limit is 0, then we have an energy density that I'm going to write exactly. So there exists phi infinity from the nodal surface. So I note like this conformal Wilmore immersion, and some bubbles from S2 to R3, conformal Wilmore immersion also. Everything is possibly branch, because when you pass to the limits, some finite branch point can appear. Such that the limit of the energy equal the energy of the limit plus the energy of the bubbles. In fact, the theorem is more precise. You have some convergence to some limit surface plus the bubble, but this convergence is up to conformal transformation, because some bubble can blow down, other can blow up. I will make a picture in a second. So I'm going to try to note one consequence is we have compactness below beta ng plus 4 pi, where beta is the minimum of W phi for the genus G surface. In fact, we have branch, and in fact, we know that also the limit of the energy is energy of the limit plus a multiple of 4 pi. This is due to, this last consequence is due to a theorem of Michelin and Rivière, who proves that if you have a branch sphere, and around any branch point, the first residue, the one given by T, vanish, then your sphere is the inversion of a minimal surfaces. But the condition to have the first residue vanishing is trivial when you are limit of immersion, because over a bubble, so if you have a bubble like this, perhaps it converges to a branch sphere. But before passing to the limit, every curve around the branch point is homotopic to a point. So the residue before passing to the limit is 0. And far from the point, the convergence is strong. So the branch spheres that appear in the limit always satisfies the hypothesis of Michelin-Rivière result.
So what is the Michelin-Rivière result?
I'm going to state it correctly. If you have omega from S2 to R3 or 4. But let's say R3. Branch, so a Wilmore immersion, a branch Wilmore immersion. Such that for every curve in S2, so we are going to branch. We note P1, Pk is a branch point. The branch point, and for every gamma in S2 that doesn't contain the point, if the integral over gamma of t, I hope is still on the board, t mu equals 0, then omega S2 is the inversion of a minimal surfaces, possibly branch. I will explain it in a second. Is T on the blackboard? No, of course not. T was the first conservation law.
Sorry. So before you erase that, can I ask you, so the thing you just erased, can I ask you that?
Okay.
So, is there, so you had this condition, lim, of something over something goes to 0. What does that mean? I didn't get that part.
So I finished the explanation. So this is the first residue, the one that comes from translation. Okay? And if it's 0, just why this is true? Because the Bryant proof says that some holomorphic quantity must vanish on the sphere. And if you are branch, the holomorphic quantity becomes meromorphic. But if you add this condition, you can erase the pole, and then everything works. That's the point. Because it kills this quantity is going to smooth everything and kill the pole. Now the second one, what does it mean? For me,
So let me ask you a question. So that quantity you wrote, you know, if it's a limit of emergence, that will be 0, right?
Yeah.
Okay. So for the quantity you wrote,
the limit is also 0, but I ask that the limit of this quantity over that the quantity I wrote was the limit of the length of the shrinking geodesic. So my conformal class is degenerating. I put an hyperbolic metric. So in the color, I have a small geodesic that goes to 0. So this is this. And T wedge phi plus H blah 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 phi. So this take a vector and nu. It's nu here, the normal. So the condition is this goes to 0. And if it's not going to 0, the interpretation I get for the moment is the same for harmonic map, is that your surface is going to split to become disconnected a priori, and linked by something that shrink to a special curve, and the length of this curve will depend on a limit like this one. In fact, this is the energy lost, and the length of the curve you have to realize this. For harmonic maps, you can build this example of tori that shrink on the geodesic. And
so in this case, you should get what, the elastic curve?
It's an open question. It's among my perspective, is to now, like for harmonic, to push the analysis in order to study the locus of concentration of those color. Or there is another option, is to exclude the formation of color, which can.
Is it understood how much energy you need to have this kind of degeneration?
This kind, at least, so I won't have time to speak about that, but here you need, the minimum you can do is to glue 2 Willmore tori minus 4 pi. You take 2 Willmore, because you need some genius. So you take a first one, a second one, but you invert it around the point. So this is the minimum you can. So since you invert it, you have 2p squared minus 4 pi. Here you have 2p squared, and you try to glue them. If you are able to do that, it will be the small level of energy that occur with this picture. And
so you expect that in the case it degenerates into elastic curve, that will carry some energy? That will take away some of the energy in the limit?
No. So no, this is the answer to the question: what is the level of energy we need? But if we lost energy, I think this example is not possible because we can't disconnect it. Here, when you glue, before you concentrate this one, and it is going to look like a plane plus a tiny thing here. And so you can identify the tangent plane here and this plane here and cut. But you can't separate it because the diameter is going to be too large. But what can happen is, I don't know, perhaps something like this with some energy loss in between. So in R3, the picture, I think it's false, personally, in R3. But if you allowed some curvature, some elastic curve to be closed, to have closed elastic curve, like closed geodesic in Riemannian manifold, perhaps we can construct this kind of example. That's my point of view. But in R3, I suspect perhaps, but it's not done yet, but perhaps we can avoid this phenomena. But before we have another one to avoid, and I'm going just to conclude.
Can I ask some more questions?
Yeah, of course.
So when in that theorem there, you say that under that residue vanishing condition, that the limit will be the inversion of a minimal surface.
Yeah.
So
with planar end.
Yeah.
It's important. There is no catenoided.
Yeah. Do you have any more restrictions on the minimal surface that you could possibly get? So meaning, is every minimal surface with planar ends? Could it be the limit of things like this?
I think no. So that was my last point. In fact, so it's a work in progress of my student, but so the simplest case, so we prove in this same paper, but I won't have time to speak about that below 12 pi, we are compact. And what makes optimal the 12 pi is the following picture. You take the chain Glascaster surface. This is a chain Glascaster surface. It's a Glascaster. It's a genus 1 surface, minimal with an n pair end. Okay? In fact, you have any genus, but let's take a genus 1. And now you inverted it. Okay? So you have a genus 1 surface with a triple point here. Triple point. And this is the simplest example of blow-up I can imagine. And now you take an n-pair. So sorry for my drawing of n-pair. With, of course, an n-pair end. And you contract it. And so the Willmore energy is 0 because it's minimal. Here it's 12 because you have a triple point and it comes from a minimal one. And perhaps you can desingularize this. This is the minimum 12 you can do. You can expect perhaps less, like if you take, I don't know, something like this plus a 4 pi. But we show that this picture is impossible because it has to be linked by something. And this something needs to be like a catenoid, and catenoid can't occur because there is no planar ends. So this is the second part of our theorem. We prove that below 12 pi we are compact, that we can join things by catenoid. But, and this is the last picture I'm going to.
So when you say below 12 pi we are compact, it means that if you take a sequence of Willmott inversions, you get inversion?
No,
What do you mean?
we are compact in the sense that if we rescale, we up to conformal transformation, of course, we converge to a limit surface and there is no bubble. But, and so yes, you're right, no bubble, so no branch point. Because branch points can develop only where there is bubble. Because else, if you have no concentration of the energy, you have Harnack inequality on the conformal factor, and the conformal factor can't shrink. So it can shrink only here, for instance. When you are going to pass to the limit, a branch point is going to, because you have concentration of this energy here. Okay? Everywhere else, it's impossible. If you have strong convergence, that the conformal factor shrink. And just to
quantify the number for the sphere inversion, what is the
16 for the sphere inversion. I come to, it's not the sphere inversion, but 16 because we expect that the min-max is achieved by a sphere. And the first Bryant sphere is 16 pi. And yeah, that's my last. So in fact, so in the blow-up that can occur, if we have no branch point, we prove that the next step is beta mg plus 12 pi in the proof. So if you have no branch point, because, so here the neck region, it's not a neck because it's also a bubble, have to be a minimal surfaces with planar end and a non-trivial one. So the first one is 4 end. So you put one end on your surface, and so yeah, you have one here, one here. So yeah, if you want to blow something somewhere, this is the first, without branch point, you need to develop at least 12 pi. And here, this kind of example are harder to exclude because it's bubble over bubble. Because here, of course, it's big, but in fact, it's very small. It's a planar minimal surface with planar end. You concentrate and you glue at each of the 4 ends 3 spheres plus your preferred surface, Willmott surface. And so here it's also a bubble. The neck are in fact the region here, but yeah, it's harder to. So yes, just to conclude, yeah, those I would like to raise those questions. And the last one, which is the interest of the residue, because for Pinkel tori, we compute this quantity, so which has the lift of elastica by the upfield vibration. We compute this, and we show that it vanishes only on the Clifford one, when the elastica is a great circle. And one question of interest is to try to understand in which way those residues characterize the fact to be conformally to minimal surfaces. Of course, it's not, they won't give a full characterization, but it can be at least a necessary condition, and perhaps more. And I'm sorry I take too much time, but thank you for your attention.
Okay, well, we've asked lots of questions, but is there anything more from the audience? So, if not, let's thank Paul again.